Hello my physics students, it's Mr. Bozide again. Welcome to another flip video. Today we're going to be talking about two-body systems. I've got a couple examples right here. This example has a special name or a specific name. It's called an Atwood's machine. And all it is comprised of is a pulley with a string, and on either side of the string are some masses. Here's another two-body system, and this is just two blocks, right? And they're going to kind of interact with each other by pushing one against the other. So when I do that, we can think of this as a two-body system. And one of the hallmarks of a two-body system is that there's a connection between the two objects. And that connection really transmits the force from one object to another and back again. So for example, in this string, we know that the force of tension in a string is the same throughout. So that means that however much tension is pulling up on the object on this side, on the right, the same string is pulling up on this object on the left with the same tension. Likewise, when we push these two blocks together, however much force this block is pushing on that block with, well, this block must be pushing back with the same amount of force, right? Interesting thing about this is that when the two masses are the same on the Atwood machine, well, gravity's the same and tension's the same. They're in equilibrium, they're balanced. But if I add some mass to one side, then that means that this side has more mass, and what we find is that it accelerates. We know when the forces are balanced, an object can either be at rest or it can move at a constant velocity. So this is pretty fun. If I give this just a slight downward constant velocity, we see that the one moves up with a constant velocity. They move with a constant velocity together because the forces are balanced, and that's, as we know, inertia. But like I said, if I hang a little extra mass on this side, then the forces are no longer balanced, and we find that it accelerates. Okay, all right, so let's take a closer look at the Atwood's machine. Here we can see it right here. We've got our two masses going up and down, and this is a diagram of it. In my diagram, you'll note that I made the second mass M2 larger than the first mass, or at least I tried to show that that was the case. As usual, the first place to start with any sort of Newton's second law problem is to draw a free body diagram. So let's start by doing that. Let's draw a free body diagram. First, we'll draw a free body diagram for M1. So it's got force gravity down, we'll call that force gravity 1, and force tension up. Then we'll draw a free body diagram for M2. It's got force gravity down and force tension up. We'll call that force gravity 2. We should be a little bit more accurate with our free body diagram, though. We should figure out kind of which forces are the same size, which forces are bigger, what forces are smaller, how do they compare to each other. Well, right now, if they were the same mass, these would all be in equilibrium with each other. But I've clearly indicated that they're not the same mass. So I've added more mass to this side, which is going to make it accelerate. And we see that happening right here, okay? So we see them accelerating. In fact, something that's really important about two-body systems is that both objects have the same acceleration. And if you think about it, that makes perfect sense because they're tied together with the string. So however quickly this is accelerating down, whatever rate this is accelerating down, the other one's accelerating up at the same rate. Watch it one more time and just kind of convince yourself that they're accelerating at the same rate. There you go. We'll remember that for later. Let's come back to our free body diagrams. How do these force tensions compare to each other? Well, we just had a nice conversation about how tension in a string is the same throughout. So that means that these two force tensions should be the same length. I'll make this guy just a touch longer so that it's a little bit more similar in length to that one. Since this has more mass and this has less mass, this force gravity should be longer and this force gravity should be shorter. So I'll go ahead and I'll fix that in a second. Before I do that, let's think a little bit about how this force gravity should compare to that force tension. You're always tempted, just your kind of intuition makes you want to think they're the same size. But they're not, right? It's accelerating. This guy's accelerating down, so this is going to have a larger force gravity than tension. And this guy's accelerating up, so this is going to have a shorter force gravity than tension. And again, that makes perfect sense because this guy's mass is small, whereas this guy's mass is large. All right? Now, here's where things get interesting. In the past, we've only considered a single object. And when we consider a single object, we just have to add up the forces acting on that object and then find that object's acceleration. Well, we can do something similar here. We can think of this, instead of two objects, we can think of it as one object. And then we can apply our knowledge, our kind of rules, our system of solving other problems to this. Here's how we can think of this as a single object. What we can do is we can kind of put a dotted line around this, and this is going to kind of illustrate that it's all one big object, right? It's just that this side of the object's moving down and this side of the object's moving up. But because it's the same acceleration, that really allows us to think of it as the same object. That really helps us to do that. So the first step that we need to take in solving this is, of course, to write out our net force equals ma equation. Net force equals mass times acceleration. Well, let's ask ourselves for a moment, what forces are making our object accelerate? Oh, we got force gravity, force tension, and force gravity. So those forces combine to make our one big object accelerate, right? What about the masses? What mass is accelerating? So it's kind of our thinking of net force. What mass is accelerating? Well, this guy's accelerating, but this guy's also accelerating. And they're accelerating at the same rate. And how does the acceleration for each one compare? As we already discussed, it's the same. So we need to think of a way to add up all these forces. And here is how I recommend you do it. What I recommend you do is you bend your coordinate system. Normally, we think of net force in the x direction and net force in the y direction. But really what we want to think about is net force in the direction of acceleration. So which way is our object, if we think of it as one big object, which way is our object accelerating? It's accelerating like this. It's accelerating up on this side and down on that side. So this is going to be our axis. If it helps you a little bit, you can do it like this. Think of this as one axis and this as another axis. If we think of that as our axis, bent like that, then on this side of the pulley, upwards is the positive direction and downwards is the negative direction. And on this side of the pulley, downwards is the positive direction and upwards is the negative direction. So that means that over here, force tension is actually a positive force, but over here, and force gravity is a negative force, which we're used to. But on this side, force tension is a negative force and force gravity is a positive force. Interesting. Now we can write out our net force equals ma. Here's how we do it. Let's see, we'll add up all these forces. So we've got minus force gravity 1 plus force tension minus force tension plus force gravity 2 equals m1 plus m2, because both masses are accelerating, times acceleration. And they both have the same acceleration. So there you have it. Now what you notice, and you know you're doing this right, is if that force that connects the two objects cancels out. And sure enough, we see that this and this cancels out. Because on one side, that force is positive, but on the other side, that force is negative. So this simplifies to negative force gravity 1 plus force gravity 2 equals m1 plus m2 times acceleration. To find acceleration, which is the most common thing that you'll be finding, is you then divide m1 plus m2 over, and I'll turn these force gravities into mg, so this is negative m1g plus m2g over m1 plus m2 equals our acceleration. And there you have it. That is how you would find the acceleration of this system. So if we knew that, like, say, m2 was 10 kilograms and m1 was 5 kilograms, then we'd simply plug in 10 kilograms, and 5, and we can find what the acceleration is. Now, what if we wanted to find the tension, the force of tension? Notice that doing this whole thing where we consider it to be one big system isn't going to allow us to find the force of tension because tension cancels out. So what we need to do is we need to then, once we have the acceleration, go back and take a look at just one of these objects on its own so that the acceleration doesn't cancel out. So for example, here's how we would go about doing that. Let's take a look at m2. Well, we could say net force equals ma on m2. Net force equals mass times acceleration just for m2. We need to, however, when we do this, we need to keep our positives and negatives aligned with our bent axis. So the forces acting on this object are plus force gravity 2 minus force tension. So plus force gravity 2 minus force tension equals m2a. This is no longer m1 plus m2. This is just the second mass. So we've got m2 times g minus force tension equals m2a. What we can do is we can add force tension to the other side, subtract m2a over. So we see that we get plus m2g minus m2a equals force tension. And now we can solve for force tension that way because, like I said, we would know m2, right? m2 in my example was like 10 kilograms. Here we solve for acceleration, so we have the acceleration, and gravity is 9.8. So we can find force tension. There you go. In summary, the way that we found the acceleration and the force tension for our Atwood's machine was to first think of the two objects not as two separate objects, but one big system, kind of awkwardly rotated around or bending our coordinate system around, but it's important, but as one big system nonetheless. Then we thought about what forces are positive and negative when we bend our coordinate system around. After we've done all that, we can apply Newton's second law and solve for acceleration because that force that's kind of connecting the two will cancel out. Once we've found acceleration, if we want to know what that force is that connects the two objects, in this case it's tension, if we want to know what that force is, we can go back here and we can say net force equals ma for just one of the two objects. For example, m2. And then we know everything we need to find the force of tension. Great, I hope this was helpful. And I've got a follow-up question that I want you to think about. Okay, now we're going to try to apply what we just learned about the Atwood machine to a new system. This is kind of another classic system, the one where you've got an object on a surface and it's got a string that goes over a pulley to a hanging mass, and that hanging mass is accelerating down, which is making the object accelerate with it. And this classic system, we kind of call it a Flatwood machine, kind of a twist on Atwood machine because this is on a flat surface. As we discussed in a previous lab, both these objects are accelerating at the same rate because this mass, this hanging mass, it's a constant acceleration because this hanging mass is pulling with a constant force on the cart. What I'm going to ask you to do right now in a moment is pause the video, and I want you to do two things. I want you to draw the free body diagram for each of these. I want you to bend the coordinate system, and then I want you to label the forces along the coordinate system as positive or negative. Before you do that, I will go ahead and I'll show you what we're going to picture as our system. So we're going to picture this whole thing as our system right there, right? It's one big object accelerating together. However quickly this accelerates down, this will accelerate to the right at the same rate, okay? So pause the video, draw the free body diagram for each object, bend the coordinate system, and label the forces along our bent coordinate system as positive or negative. Remember, we want to bend the coordinate system in the direction that things are accelerating. Give it a shot. Okay, I hope you tried. Here's the answer to that question. The free body diagram for this guy, we're going to assume it's frictionless, so it's going to look like this. He's going to have force gravity down, force normal up, and force tension pulling him forward. This guy here, he's going to have force gravity down and force tension pulling up on him. Now again, if we think about this, this force tension must be smaller than this force gravity because he's accelerating down. And these two force tensions should be about the same length because it's the same string. Now here's how you're going to want to bend your coordinate system. You're going to want to bend your coordinate system like this. Just like that. That's how you're going to want to bend your coordinate system, okay? Now that we've bent our coordinate system, we can identify what forces are along the coordinates, along the axis of acceleration. Well, just force tension is along that axis here. Force normal and force gravity are not pointing along the axis that things are accelerating. On the other hand, for the hanging mass, both these forces are along that axis. So anything that points to the right here we'd consider positive. So this force tension is a positive force. And anything that points down would be positive. Anything that points up would be negative. think that's all the advice I'm going to give you. From here, I think you can solve for the acceleration of this system symbolically. So do two things. I want you to find the acceleration of the system, and I want you to find the force of tension in the string. That's your homework. See you tomorrow. Bye.